Great, thank you guys. I'm very happy to be here and thank you for coming. I would like to share with you what is actually my big passion. I spend a lot of hours every day at the company working on this because I think this is really cool. I discovered this, I think, was 5 years ago. I was seeing one of Sebastian Trun tech talks, and he was talking about autonomous cars. And he said that when he was 18, he lost his best friend on a traffic accident, and actually, I almost lost my father in a traffic accident. I was very lucky that he didn't die, but I was very close to that. And then I said, this is something really cool. This combines things that I wanted to work on, that was robotics, and this combined also something that I could dedicate my life to make life for other people better, right? So I would like to start my presentation sharing with you this video.
Ask a girl what she wanted to be. She said, baby, can't you see? I wanna be famous, a star on the screen. But you can do something in between. Maybe you can drive my car. Yes, I'm gonna be a star. Maybe you can drive my car. Maybe I love you. Beep, 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 yeah.
So there are plenty of commercial videos out there to promote self-driving technology, but I think this is the best one that I found. This is from Mercedes-Benz, and is where I completed my PhD last year. So when I saw this video, I would really like to see this sometime happen. Probably soon, probably not so soon, but at some point I would like to enjoy to see some kids like in the driver's seat, right? But when I started like getting to know about autonomous driving, I thought it was pretty a new idea, right? So I thought, oh, there is like the robotic revolution, and people start to think about how to apply this to cars. But this is actually not the case. This came from so early, like 1940s, where people start to think, okay, we have highways, and we would like to automate our highways, right? So we would like to see cars without drivers on. Without drivers, we would like to spend time doing something different than driver while commuting. And people start like dreaming about this, but at that point, like 100 years ago, was just that was a dream, right? Um, and then people like started working on this, and I would say that one of the first projects that really showed self-driving capabilities was in the 80s, and was done pretty much at the same time in the US and in Germany. In the US by the Carnegie Mellon University, where they had this blue car, and they were putting some sensors on the top. And then at the same time at Mercedes-Benz, together with a university in Munich, where they were also trying to do self-driving cars in the highway, right? So one of the, as you may know, Hinton is is called the godfather of deep learning, and there is a professor in Munich who is called the godfather of self-driving cars, and he was leading basically this project over here. But again, this was like a pretty much an early stage, and what really changed the game here was the DARPA challenges. So the DARPA organization in the US said, okay, we would like to sponsor a challenge where teams from very famous universities like MIT, Stanford, and so on work on self-driving technology, and this we could use for our applications, right? So basically, the Grand Challenge was the first one, 2004, and the goal was to drive through the desert, but no one really ends achieving at that year the goal. So a lot of cars were just in the middle of the road and couldn't go to the last stage. So they say, okay, let's try the next year again. And the next year, actually, there was one car that finishes, and that was from Stanford. And then people say, okay, so the teams are getting better, and this is getting interesting, so we have to increase complexity. And the idea of increasing complexity ended up with the DARPA Urban Challenge that was pretty much the same, to go from point A to point B, but having more complex interactions within a city environment. And in that challenge, the winner was the Carnegie Mellon University. The team was led by Chris Ursom, and Chris Ursom has been the lead of Google self-driving cars for a lot of years. And the second one was Stanford, and the lead was Sebastian Ramos, and he was also the one that started the Google self-driving car project. So basically, the story is like they meet with Google co-founders at the end of DARPA Urban Challenge, and Sergi and Larry said, okay, we would like to put a lot of money here and see if you can do something working out of here, right? And this is how it looks right now. So a lot of tech companies and a lot of automotive companies working on this field from different point of view with different approaches, but trying to reach what I showed at the beginning. But then why do we work on self-driving cars? It's just for fun. It's really fun, as Eric said today in the morning, but it's not really just for fun. The first thing is we would like to have safer roads. We would really like to have a reduced number of accidents on the road. And I know media has been showing these accidents that we have recently seen, but we have to think that, I mean, this is just a couple of accidents from millions of people that die every year by human accidents, right? So we really have to reflect on this, and I think we have to, if we put some robots on the road, we really have to make sure that they are safe robots, but on the other hand, it's pretty difficult. It's the main challenge that we are facing right now. We can do pretty nice demos, but having these safe robots, know that they are safe enough to put them on the road is the big challenge, right? The next reason is to have mobility for everyone, for the kid of the video, for someone that cannot drive anymore, and so on. The next one is about comfort. So in cities like Los Angeles, people spend a lot of hours in commuting every day, and you would like to spend these answering emails, reading, and so on. And the last one is about improving mobility. So imagine you buy your self-driving car, you go to work, and then the car comes by itself back, and then pick up your wife, and your wife can also go to work, and then again the kids to school, and so on, right? And the question is, okay, we would like to go there. These are the reasons why we would like to go there, how we can really achieve the self-driving cars. And then one of the things that people have tried is to do this end-to-end approach, what Eric was mentioning at the beginning of his talk, to have a module that get input all sensor data and the output is like the driving commands, right? But what we are trying to do is what we think that is the right thing, and here there are two different variables that we need to take into account. The first one is there are levels of automation. So we can say, okay, we really want a car without a steering wheel that do the whole driving, or we can just have some system that help us with the driving to make safer, right? And also the scale and scope. So do we want just to drive, for example, a certain series, or do we want to drive everywhere? Do we want to have 10 cars on the road? Do we have to 1,000 cars? About the levels of automation, so the industry have defined 5 levels of automation, going from just driver assist systems to help the driver to fully automation. And there are mainly 3 scopes here. So a prototype where you test your cars in controlled conditions. Then you have a fleet, like a Google self-driving car, driving in very specific cities in the US. Or you could have mass deployment like Tesla, that the aim is to drive everywhere, right? And from this come like 2 main approaches. The first one is incremental automation. So you would like to go from level 1 to level 5 incrementally. And the second one is direct full automation. You would like to approach as the full automation problem, but then going from prototype to mass deployment in an incremental way. So it's like 2 orthogonal ways of approaching this problem, and different companies select the one that they think is the best one, right? And then thinking about how the autonomous car works. So basically, let's imagine you are the car, and then the first thing you would like to ask yourself is, okay, I'm alone on the road, or there is something different that I have to take into account? So are there any objects in the surroundings? If so, you would like to detect the objects, and you also probably would like to extract other information from your environment that is important for this task. I'm going to talk about a little bit later about this. Then normally, as a driver, if you want to go through Gothenburg and you don't know the city, then you think, okay, I need a map like Google Maps, and cars also have maps, but these are a little bit different maps with different information that are needed for the driving. And so you would like to localize your car within this map to take into account this information that you have stored in the map. And then the next one is, okay, if there are some other cars or pedestrians or whatever on the road, what the car thinks that these people or these cars are going to do the next time or the next few seconds, so that you can plan your trajectory. And this is called like predicting what the other traffic participants are going to do. And the last question, of course, is, okay, I have extracted all information, what should I do? What should be the movement or the trajectory that my car has to follow? Great, and talking about a little bit more about the topic of the talk is perception, so how really self-driving cars perceive the world. We have cameras, we have lidars, we have radars, and we could have other sensors, but I would like to focus in on this because these are like the main sensors for the perception stack. And here we see a camera where you see, okay, you get 40 images per second, and in each image you have 2 million pixels, right? Then you have the LiDAR, where you have a 3D reconstruction of your environment with depth measurements and reflections. And then you have radars, where you have measurements of moving objects and the speeds of the object, right? And the question is, okay, what can you do with this, and how would you like to approach this processing of information? So let's take a look at this. You have sensors. You could have X number of sensors, and then you can process the data in different, like independently modules, where you say, okay, I would like to extract like bounding boxes, as you have seen in Ericsson, for the moving objects, right? One for camera, one for LiDAR, one for radar. And then you would like to fuse this information, and you could do it. You could fuse the process data. You could fuse bounding boxes coming from cameras, bounding boxes coming from LiDAR, or you could fuse all sensor information first and then try to predict your bounding boxes on this fused sensor information. So there are mainly two different ways of approaching this. And then again, the localization part, where you have the map, and you could do it in a raw data level or in a process data, and what you want at the end is the environment representation for allowing your car to plan what their trajectory, right? And of course, deep learning can be used here, as well as in sensor fusion and localization. And I would say that in all modules you can use deep learning, but there are different stages of the state of the art. So in data processing, it's really advanced. We as a part of the industry, we don't really believe that without deep learning you can do what you aim to do in the data processing. Then sensor fusion is something that people have shown really promising results with deep learning right now, as well as localization, and we are working right now on this. And then I would like to show you one example of what was live before deep learning. So I started, this is an example of my master thesis, that was 2013, and I was trying to predict for each pixel this set of classes that you see here in the bottom part, right? And this would be a really nice representation for a self-driving car. The problem is that I couldn't use deep learning at that time, so I was using super vector machines with handcrafted images, features, and graphical models. And you see a very brief understanding of the scene. So in the bottom part there is the road, in the top part there is the sky, and so on. But it's not really fine enough to really give the autonomous cars the capability to drive themselves. So it's really hard to distinguish between sidewalk and road and so on. And these are things that are really, really important for the driving, right? So at that point was, okay, really nice research results, but we cannot put it in the car. We cannot really do anything with this. So you could do some videos and show some results, but nothing more than that. And then came deep learning, and with this the need of a lot of data and very precise annotated data. And during my PhD at Daimler, we created a data set called Cityscapes, and the idea of this was having more than 10,000 more than 1,000 images with this kind of annotations, and the results that we're able to get were like this, right? So this is actually a scene in Gothenburg where you see that you can distinguish between the grass and the sidewalk and the road. You can also segment the cars and so on. And at this point, this really changed the game, because at this point we said, okay, then with cameras and with deep learning, we can really do something that can go in the cars, that can run real time, that can be useful for planning our trajectory, to know where we can drive through and so on. There are mainly two drawbacks of this approach. The first one is you really need really nice annotations of all pixels in the images, and it takes a lot of time. And if you really want to cover a lot of different scenarios, you need a lot of images, and then it costs time and money. But then you have corner cases, and everything about deep learning, at least for self-driving cars, and I'm pretty sure for other applications, is about the corner cases. And with corner cases, I mean this kind of images. So here is a car, but the car looks a little bit strange. So the network is not able to say this is a car. So part of the car is segmented as a traffic sign, the other part is segmented as a pedestrian, and so on. And then the car is really, your self-driving car doesn't really know what it is, right? So you need to come up, if you want to have a safe system, you need to come up with solutions for this, right? And at Zenuity, we develop, while we are working on deep learning and deep neural networks, we develop also algorithms that are able to cover these corner cases. So we see here, this is the same car, the same strange orange car, and with a parallel approach, we are able still to say, okay, this is a car, we don't want to hit this car, we don't want to crash against this car, right? Another approach that we could think about is, okay, we don't want to put a label per pixel in the image because this costs a lot of money and time. We would like just to do this for the free space, and for everything else we put bounding boxes around this, right? So you see here the cars that have some bounding boxes around them, and the free space is segmented pixel by pixel, giving information about the lane marks, the drivable road age, and so on, right? And these are two different approaches that you could, they have some advantages on both sides and some disadvantages as well. But again, the case is not just driving in very nice weather conditions. You in Sweden have really tough weather. I would say most of the time. I come from Colombia, so I come from a country where the weather is really, really nice. But I lived since 7 years in Germany, so I know that snow and weather is not really nice in Europe, and could be in Colombia. But we have to make sure that, for example, in Colombia, I cannot imagine self-driving cars like driving around, because people don't really care about traffic rules. People drive like crazy. Here in Europe, it's a much easier problem from this perspective. But on the other side, you have this problem of the weather conditions, right? And we can take a look at the other video. Here we see it's raining, and you have problems with the reflections on the road. And then the question is, okay, what is the limit of your model, of your deep learning model that you develop? Is this still good enough to perform the task that it's supposed to do, right? So we develop some models, and then we test this until we get the limits, and then we start to think about, okay, these are the limits, how we can go forward, how we can extend these limits to cover more and more situations, right? And I think it's really interesting what deep learning is generating this community or in this space, because when I started with computer vision and with machine learning, there were certain problems that you say, okay, I have to apply some learning algorithms to solve this problem, like for example, detecting pedestrians. The idea is you learn some model that take advantage of the appearance of the pedestrian and is able to predict pedestrians, but predicting depth from images was not something that you would solve with deep learning. It was something that you would solve with geometrical cues. Like humans, we have two eyes, and we can triangulate, and we can get measurements of distance from that, right? So in the car, you could also have two cameras, stereo camera, and get some distance estimation from the stereo camera. And deep learning is now allowing also to create deep learning models to do this what before was not really possible. And not just the estimation of depth, for example, estimation of optical flow. Here we see in the different colors that the pixels that are on the car are moving to a different direction. So the idea here is for every pixel you estimate the flow, the optical flow, in which directions they are moving in the next frames, right? And then, of course, it's not really enough to work with cameras. It's like very intuitive to work with cameras. We as humans have eyes, but then it's also very important for safety cases to work with other sensors and to fuse information and get robust enough systems. So this is a project that this is the main focus of my team in Munich at Zenuity office in Munich, and the idea is to combine different sources of information and have deep learning models that can handle this kind of different sources of information to produce very accurate estimations. For example, here the 3D detections of cars. And then this is an example of one of the results from my PhD at Mercedes-Benz. This example is, I pick up this example because this was something that I will never forget. I was given a task during my PhD, I was given a task of detecting small obstacles on the road. And at that time, this was 2014, no one in the world, no one working on self-driving cars could solve this problem really with cameras. So my supervisor, who is really a famous guy in this autonomous driving space, he said, I would think that the maximum distance that you can detect these objects is 100 meters, because he came from the geometric background. So he was working a lot with the stereo camera. You see that in Mercedes-Benz cars, there is a stereo camera, and he was the guy putting the stereo camera there, and he said, I don't think that, so we create a data set with maximum distance of 100 meters, and this would be like the limit of any algorithms that you could create. And after some time using deep learning, I showed this video to him and say, hey, Uwe, here are the results. We can segment objects farther away than 100 meters with just mono camera. And this was pretty amazing. And the main difference between this and what we have seen before with the semantic segmentation is that, okay, if you define a set of classes like cars, pedestrians, sidewalk, you really know how these look like, right? So you know how pedestrians look like, you collect data from pedestrians, you train your deep learning model, and then you test and get recognition of pedestrians. But in this case, the problem was about, I don't know what object could be in the road, could be anything, could be a kid lying on the road, could be a bicycle lying on the road, could be an animal, a plastic bag, whatever, but I would need to recognize this. So you cannot create a data set, a data set that covers all possible objects on the road. So you need to find other way to do this. And in this case, what the idea was, okay, I don't know what I'm going to see on the road, but I know that what I'm looking for is within the road. So the neural network should be able to leverage the context and look for something on the road that doesn't look to be part of the road. And with this, we got these results. But then we need to test this on corner cases. And this is one of the, I think, best examples of corner cases for this approach. Paintings on the road that doesn't look like normal paintings, like lane marks. These are paintings that someone created. And then it was pretty amazing to see that the network was able to generalize and to avoid false positive detections on this kind of roads. And also what was pretty cool is we got also to drive and collect data during night. And then without putting any object to test our approach, we got situations where there were indeed some objects on the road, and then we said, okay, let's try our approach. And we saw that actually during the night also we were able to detect these small obstacles on the road, what was really, really amazing for us. And again, about what the corner cases here, so I was taking a look at this sequence, and at the beginning I thought, oh, it's not working really well. There is a false positive there, but if you really look close to the image, you see there is a bird flying through the road. And then you ask yourself, is this really the output that I expect? Is this a bird flying through the road, a small obstacle on the road? So these are the limits because you tell the network what you would like to expect, but at some points, I haven't thought before about this really. So it was pretty amazing to see this. Or the next example, exactly the same. I thought, oh, some false positive down farther away in the image, and actually it was not. So it was actually in the middle, one birth, and in the left side, other birth that were. But I mean, we can ask ourselves, should we be able to test this? And I would say yes, because as much information as you get, better would be the things that you can plan for your car to do, right? And of course, then if the question is, okay, you have a network that can generalize over different cases, and you are looking for the corner cases, what you can do is to try to use synthetic data for cover these corner cases. So Eric was saying simulation is a pretty important tool for us, and we can go in two different directions, right? We can try to simulate the whole world and put whatever we want in the world, like a lot of cars, simulate different kind of sensors, so you can simulate cameras, you can simulate lidars, and so on. And here, the nice point is that you get automatic annotations from this kind of data. So you could train your networks using this data, and you could also verify your networks without having people annotating this data. And this is really important. This saves a lot of time, a lot of money, and then you can cover more and more things that you can imagine on the road. So one day you can wake up and say, oh, probably I could test this, and I could test that, and so on, right? Without having to put things on the road. So I have really a lot of troubles to generate a first data set for these on-road obstacles because I had to close the streets, I had to put some things on the road. Actually, it was pretty funny. At some point, I wanted to create some data set in a residential part, and I put some things on the road, and I drove the car, and when I came back, the things were not there. And I was like, what? I'm in Germany. Who stole this? It doesn't happen like here. And then I saw there was a grandmother that thought that it was trash, that the trash car left on the road, and she was just putting this away from the road. So it's really, collecting data for some task is really not an easy task. Annotation is really hard, but also the data collection is something that at some point is really hard. Great. The other thing that you can do is to have normal data and try to extend this data with synthetic data. So you see here is images from real scenes, and you put pedestrians within these images, and then you can train your models, you can test your models, you can use different poses of the pedestrians, you can play with a lot of factors here that in the real life would be a little bit difficult to do, right? And this is something also we are working on, and we believe that this is something that should be considered in order to cover all these corner cases, what is actually the key here. Great. About the current challenges, so I would like to talk a little bit about what we are working on. It is not like, okay, we solve everything with deep learning. It is actually not like this, but we are on the way, I would say. One of the things is uncertainty. It's really important to get uncertainty about the predictions of your models, and it's not actually something trivial. You could say, okay, the predictions are so good that you don't really need this, but if you want to put some robot on the road and you then say to the robot, there is an object like 50 meters away from you, you really want to know how certain your network is about this prediction, so that you can say, okay, I have to slow down, or I have to change my trajectory or something like this, right? And this is not really an easy problem with deep learning. The next one is about the open set problem. So if you train a model and you say, okay, let me select 10 classes, and please give for each pixel of my image one of these classes. What about if, for example, you are driving and you find some elephant on the road? Is there any, you didn't put any elephant class, right? So what is your network going to do if it sees an elephant? Which class is going to pick? And this is called in the community the open set problems, and it refers to the fact that there could be classes that doesn't belong to the set of classes that you define, but then you would need to come up with a strategy to describe these classes. For example, saying, okay, I would like to describe this not as an elephant, but as an object on the road that is moving, whatever, with attributes, basically. The next one is functional safety. This is something that actually, when I was doing my PhD, I really didn't hear about many times, because it was like, okay, you are doing nice research and get you doing this, but now that I'm working at Zenuity and I really want to put the things that we are doing on the car, every time come a functional safety guy and say, hey, you are doing really nice videos, but is this really safe enough? Is this really something that we can use in our cars? And then they ask me a lot of questions, and I say, oh, that makes a lot of sense. And this is something that we really need to get to make sure that we can cover these functional safety criteria to put something on the road. Because we are not developing deep learning models for voice recognition in a phone, right? Because if it doesn't work, well, probably you get angry. You could try to broke your phone. This is the worst case I could think about. But if this goes wrong, you can really have do damage to human life. And this is mainly the big difference here, right? And then about the generalization. So if you want to have cars in Gothenburg, they have to work not just in sunny days, but also when it's snowing, not just during the day, also during the night, right? Because one of the normal cases that I always have been asked from my friends is, could your cars drive me when I'm drunk? And you go drunk at 3 in the morning, so the lighting conditions is not the best one, and this is something that we have to think about, not just during the day, during the night, and so on, right? And again, everything is about corner cases. This is one of the take-home messages that I want to give you. And about other take-home messages, I try to summarize this in 3 steps. The first one is, yes, deep learning has enabled really great progress in self-driving cars, but it's not everything solved yet. So we really have a way ahead to solve everything. And the main point is, the main gap right now is to bring this on real cars, is to make this safe, because we are dealing with human life, and this is really important for me and for a lot of people that work with me at Zenuity. I wanted to show you these images. I did a live demo at NIPS 2016, and I wanted to show you this because NIPS is a very theoretical conference, machine learning conference, but people are really getting more and more interested on seeing what they write in papers, to see it running on cars, to see it really doing something, working in an application, right? And it was really nice to see a lot of interest from very theoretical people. And then just to finish, I would like to finish with this slide, what I was talking about before, the elephant, and then I have my, let's see, for example, semantic segmentation network with my predefined classes, and I ask, okay, what do you think that the network is gonna pick? But you don't have any road classes. Okay. Some other guess? What? Okay, pole, car. Okay. And what do you think? Why do you think that pedestrian?
One reason is it's moving across the street,
Okay.
so the direction fits.
But this is just based on the single image, right? So you don't have any temporal information.
You have cars in the background that I guess your network should be able to recognize.
Mm-hmm. Okay.
And this elephant is not really facing the cars I'm looking.
Mm-hmm. Great. So actually, this image came from my supervisor during my PhD. He was in a neuroscience conference, and he was giving a talk. He was sitting next to a neuroscience, and the neuroscience asked him, hey, what do you think that would happen in this case? And then 5 minutes after, I got an email from him and say, hey, could you run the network here and get me back with the results? And I saw like, what? Hey, I'm working. But this, I have to say, this was a pretty nice experiment, and the result was this one. And then you can say, okay, the elephant has still legs and has eyes, and you could think about this, why really is the case, right? If this is right or not, I would say, yeah, it's the best guess that it could do, but I don't know if this is enough for us for driving autonomously. Great. Thank you so much for the talk.